Yes, thank you for letting me come a bit earlier in the process. So actually, I'm not the CEO. It's Esben who is the CEO of N2MO, and he will be representing us after the session for the panel discussion. So I have got the opportunity to present the platform which N2MO has, and that's actually a platform which is based on insects. And what we do with these insects is that we are using them as model species. So this is actually to try to get better results faster, such that we optimize our drug discovery process. And what we do is that we extract the brain from a grasshopper, is the insect which we are using, because it has such a big brain, such that we can make quantitative measurements of the brain concentrations. And what we can do with this is that we can actually do a very thorough measurement of the brain penetration and have a look at the uptake profile. And the reason why we can do that is that we can take out the brain of the insect and then we can place it in a well. This means that we have all the exterior conditions, they are under full control. So we kind of have this ex vivo system where we can control the time of exposure, the concentration of exposure, and even the temperature, if that's what we want to do. And we can extract the brain because the insect doesn't have any vascular system, so we don't have any problems with residual blood and compound which is in the brain. And the fact that we're using an insect makes us able to use only tiny amounts of compounds, so we don't need the chemist to go back into the lab and to do any resynthesis. And moreover, that's kind of surprising to me. We have a very high reproducibility, which I really didn't. I didn't know whether that would be the case, but we certainly do have a high reproducibility. So we have a very small standard deviation, and that's even over a long, long time. So what does the locust look like? The grasshopper. It looks like this, and what we can see here is in the blue we have the brain. And when we chop off the head and extract the brain, then we get a picture of then we have the brain as it's seen up here. So this is the brain which we're working with. And as I said, we're chopping off the head here, and then we're taking out the brain, putting it down into a well, which contains the compound of interest. And then after a certain period of time, we measure the compound concentration in the insect brain. And this chopping off the head and extracting the brain takes around 1 minute. So it's a pretty high throughput or medium throughput method which we have. And a technician can do, I would say, 6 compounds a day, because we're using 6 brains for each data point. So why is it we can use the insect? Well, the insect has been used for many, many years as model species and it has allowed us to discover many things about the mammalian system. And we can see that the insect brain consists of glial cells. So this is actually an insect or a brain where we have real brain barrier consisting of brain cells. And the fact that we are using the entire brain makes it really unique. And we can also see that the insect brain has a lot of cells and nerve cords. And the fact that it has pretty much lipids, which is also the case in mammals, makes us able to get results which are pretty similar to mammals, because there are a lot of compounds which we know binds to lipids. And that's the case both in the insect brain as well as in the mammalian brain. I'll come back to some of this lipid binding stuff a bit later. Moreover, it has been, there are so many studies around the insect brain, it's amazing. But it has also been shown that the insect glial cells contain a lot of transporter systems. It's both ABC transporters as well as SLCs. And we can also see at the functional level that the insects, they are show same pattern as mammalian system. So this is just a snapshot of some of the compounds which we have tested. Now we have been running this model for a couple of years, so this is just a few of the compounds which we have tested. And we can see that there is a clear separation between the CNS drugs, which we have, or compounds which are active against CNS-related diseases. They are certainly more in the insect brain than those which are peripheral acting compounds. So that's pretty nice to see. But we also needed to benchmark our compounds against some of the existing models out there. So what we have been looking at initially is the rate. And if we're talking about the rate, then it's also, or we were talking about the rate because we wanted to benchmark our model with in vitro models. And this is a plot of some compounds which have been tested in MDCK cells. And if we plot these MDCK permeability coefficients against the log PS, which is the in situ rat perfusion data, then we hardly see any correlation. And the rat perfusion data that should be really the gold standard. If we look at all compounds, then it's certainly much better correlation. And if we have a closer look at some of the data or some of the compounds which we have tested, then we can see a compound which is like warfarin, which is peripheral acting. It's one of those that has the highest permeation in the MDCK cells, while compounds like fluoxetine and amitriptyline, which is known to be CNS drugs, they're pretty low. So this makes us really sure that we need really to consider the data which we're working with. And it's not always that these in vitro models, they are giving us the right answer. And this was actually the reason why we started using insects, because we were not really satisfied with the data which we got from in vitro models. But it's not only a question about permeability, it's also a question about transporters, because if we want to have a drug inside the brain, then we also need to make sure that it isn't effluxed again by transporters. So we can show it in various ways that we have transporters. We can do it in terms of co-administer with verapamil, which is an inhibitor, or we can do it by make a temperature reduction. So by doing a temperature reduction, we extract all energy from the system, and then we can see for a compound like carbamazepine, which shouldn't be effluxed out of the brain, here we don't see any transport-mediated difference, or we shouldn't see any transport-mediated difference. So assuming that this is just, or if we have a look here, then it's 30 degrees Celsius this, and we see a very high uptake of the carbamazepine. At 2 degrees, we still see a high degree of uptake, and we see a difference because of the lower diffusion rate due to the temperature reduction. However, a compound like quinidine, which is known to be effluxed, when we increase when we reduce the temperature from 30 degrees to 4 or to 2 degrees, then we certainly see a higher uptake of quinidine. However, if we add quinidine and the Pgp blocker verapamil, then at 30 degrees we see a high uptake. And again, because the efflux, it has already been inhibited by verapamil, then we just see the diffusion decrease. So this makes us really confident, and there are also a number of homology studies where we have investigated the homology between transporters in grasshoppers and in humans. And I haven't got the time to show these today. So we are pretty sure that we do have these efflux mechanisms ongoing in our model as well. However, it's not only the rate which we want to investigate. We also want to see what is the extent of the brain uptake. And if we want to investigate the extent of brain uptake, then we need to investigate what is the brain concentration over time. And the problem by using in vivo models is that when we inject a compound, then we see initially a high concentration, which is then metabolized. So when should we measure the brain concentration? Is it here or is it here? And then we always do a BP measurement. And it's really hard to do in vivo systems. in the insect system, we have a constant exposure concentration. This means that we can just select the some couple of time points, and each time point takes pretty short time to measure. So it's pretty easy for us to make an uptake curve over time. And we've done this for several of compounds. If we have a look at some of the more polar compounds like quinidine and caffeine, where we have just a small fraction of binding to lipids in the brain, then we can see that we reach equilibrium pretty fast here. While these compounds, which are intermediately binding to tissue, carbamazepine and risperidone, they are reaching equilibrium in a medium time, while compounds which are tightly bound to tissue in the brain, they are not reaching equilibrium within the time which we have measured. And this is exactly what we see in mice as well. The more tissue binding we have, the longer time it takes before we reach equilibrium. And as a drug discovery person, then I would love to see what is the free concentration in mice, and how does that correlate with our estimated free concentration in insects. And we get a picture like this, and it is quite encouraging to see such a picture here. So what should we use the insect model for? Well, we know that the way we do it today, when we are doing drugs against CNS-related diseases or any disease, then we make a compound design, and then we make the compound, and then we test the compound, and then we evaluate the data. And then we decide, well, should this compound be progressed or shouldn't it be progressed? And this just costs a fortune if we miss this point here and throw away a good compound. So it is really important that we have the real and good data to work on. But it's not only in the progression process where it's important. It's also in this process when we're feeding back the data into the design process. As we spoke about earlier this morning or earlier today, is that probably now we've been working with these traditional compounds where we have a certain number of hydrogen bond donors and acceptors and so forth. And we have been working within Lipinski's rules so much, but perhaps when we're talking about inflammation or infectious diseases, here we certainly need some compounds which are probably a bit outside the chemical space which we have been used to work in. And here it's certainly of very significant importance that we do have real good models to work on. And if we get rubbish data here, then we get rubbish compounds here. So we really need to have good models early in the drug discovery process. So just to wrap up a bit, so what we have in our model and the reason why we think that using insect models in the early drug discovery process is actually mandatory in order to get some new drugs which can give us some, which can fight the infectious diseases, is that we have the biologic active intact brain, which is really unique in this model. We have constant exposure conditions. We only use the stock solutions, and we can have fast feedback of data for the chemist who can make the next compound and really keep up the pace when we are doing new drugs. We can both make the rate, and we can measure extent and so forth. And we also have transporters in our model. So at the end of the day, I really think we have a model which contains a lot of good things here. And we ought to really consider the models which we are using in the early drug discovery phase, such that we get the real good data to work on. And actually, I think that was about it. Of course, we've been working a lot together with a number of universities and other collaborators, University of Copenhagen in Denmark and University of Lund in Sweden, and some of private organizations and Lundbeck as well. So I think that was what I had to say about the insect models.
Thank you very much, Peter. Thanks.